All right, so here we go. We are going to finish the discussion about the lines and the planes so that everyone can be on the same page on this topic as we move forward. So equations of lines and planes. So the place that we left off was that line in the XY plane is determined by a point on the line and the direction of the line, which gives the slope or the angle of inclination. And then you can, from this, get the point slope form. So that's if you have a 2D case. So in 3D, we have a line L in 3D space. And we're going to generalize that, and we're going to say, okay, so I'm also going to know a point. So this will be x0, y0, and z0 on L, so on my line, and the direction of the line. And so in 3D, we get the direction of the line by a vector. And so we'll say that this vector is parallel L. And so we will say let P of x, y, z be an arbitrary point. On L, and these two vectors r0 and r, the position vectors of p0 and p. And so what we mean by that is that they have representations if we were to put them in 3D space of origin to point p0 and origin to point p. So if A is the vector with representation in 3D space from P0 to P, then this R is equal to R0 plus A. So let's look at a figure really quick so that everyone feels clear on this notation where it's coming from. So here we have X, Y, Z, we have some line L in 3D space. We have some point here on the line, and this is point P0, and its coordinates are X0, Y0, Z0. We also have another point up here on the line. This is point P, and it's X, Y, and Z. And so we could draw, like they say, the representations to OP0 and to OP. And so this one that goes from O to P is, or sorry, OP0 is R0, just like it says right here. And then from O to P is going to be R, like it says right there. And this vector then that goes from P0 to P is going to be A. So then we say that the R, which is over here, is equal to this original one, R0 plus A. And you can see that even if you go back to the vector notation that we just did in class, you can see that here we have some vector because it's R0, and then where we go from 0 to the end point, and then we put the next vector going from this end point to the next one, and then the sum is going to be between those two. So we can see, yes, R is equal to R0 plus A. It's all in accordance with what we said. But we also know that A and V are parallel, which means by definition that therefore, I'm going to use this little symbol to represent therefore, there is a scalar T such that this A is equal to T times V. And so this means that we can write the equation of the line like this. So this is going to be the vector equation of the line L. So for every value of this t, we get a new position or a vector r that then points to a new point on the, or its representation then points to a new point on the line. So as we vary t, we can trace out every single point on this line. And so you can see that if t is positive, we're going to get the points that are on one side of r0 over here. And if t is negative, we're going to get the points on the other side of, or not r0, p0, on the other side of p0. And so this means that, let's say that this r of t, say that this r0 is equal to x0, y0, and z0, and that v is equal to a, b, c, then what we can get is something like x is equal to x0 plus at, and y is equal to y0 plus bt, or this is an equal sign. And then and z is equal to z0 plus ct. So these are the parametric equations of the line. Parametric equations of line L through point P0, x0, y0, z0, and parallel to v equals ABC. So you can see that, that this parametric equation encodes as the first coordinate, it encodes where the point P0 is, and then it encodes these second points, which is the vector that's parallel. But of course, this is not unique. You could choose a different point P0 on this line, and then that will give you a different x0, y0, z0, and then you would be able to also choose like a different parallel vector, and that will give you a different ABC, but you'll still trace out the line. It's just not a unique representation. So so the next thing that we want to say is, what does it mean though if we put it in a symmetric equation? So in this case, we could solve all of these for t and set them all equal. And so if we do that, we get these new set of equations. So this is if we solve for t in the first equation and then say, okay, all the t's are equal, so it's y minus y0 over b is also an equal sign. For the second equation, equals, notice this pen is very temperamental in ways that are inexplicable. And okay, not sure. Well, I'm just gonna try to say equals. Okay, this is equal to z minus z0 over c. And so these are the symmetric equations of the line. And so, so these you can imagine potentially helpful. And then we can also say that the line segment from R0 to R1 is given by R of t is equal to 1 minus t R0 plus t R1. 0 is less than or equal to t is less than or equal to 1. Okay, so then if people want to see a quick example, so find the parametric equations and symmetric equations of a line that passes through A at 2, 4, -3, and B at 3, -1, 1. And then, so we're not given explicitly the vector that's parallel to this line, but we can get it because we can say that the representation AB is going to be parallel to the line because it's on the line. So then that means that we can get a vector V as equal to AB, which is going to then equal, we'll do 3 minus 2, and then -1 minus 4, and then 1 minus -3, so 1 plus 3. And so in the end, we get that a vector that's parallel to our line is this one. And then we say, oh, okay, then also we have these as the numbers that we're going to have important in our formula. And then we're going to take, let's just take this point, one of the points on the line, let's call this P0. So then if we do our parametric equations, we have x is equal to our initial point in the x coordinate. So this is 2. And then we're going to say plus 1 times t, so plus t, y is equal to 4, which is this one, minus 5t. And then the last one, v is equal to -3 plus 4t. So then here's the parametric equations, and the symmetric equations are if we solve each one for t, and then that is going to equal y minus 4 over -5, and then this one is equal to z plus 3 over 4. So then you can see the idea about what is sort of the shapes of lines in starting to move into higher dimensional spaces. And then let's talk about planes. So then for a plane, a line in space is determined by a point and a direction, as we just saw. But for a plane, what determines a plane? So we can say something that determines, something that does not determine a plane is a single vector parallel to the plane is not enough, for example, to convey the full direction of the plane, because the plane is going to, the plane is like a whole plane. So a vector perpendicular to the plane does completely specify its direction. So we're going to need a vector perpendicular to the plane. I'm going to use this to represent perpendicular to the plane. And then we are also going to need a point P0 of x0, y0, and z0. So this vector perpendicular to the plane is this normal vector n. So it's going to be orthogonal to the plane. It's called a normal vector. And then we can make our brief drawing, help everyone just reorient yourself if you haven't done this for several years. So here's x, y, and z, and then we can have some plane. Sorry for this art. Then, so here is the vector normal to the plane. So here's like maybe the 90 degrees, not maybe my best drawing. Maybe I should have drawn it a little slightly different, but you get the idea that here's my normal vector. And then I also have a point P in my plane. So here's point P, which is at x, y, and z. And this one has this representation from the origin to P. And then this is my vector R. Here's the origin. And then I have this other point here. So this one is P0, x0, y0, and z0. And then, so this one is R0. So you can see that now we're able to say, okay, from our point P0, which is here, and then we have a normal vector, then we're able to know where all the other points lie in this plane. So let P of x, y, and z be an arbitrary plane, or sorry, be an arbitrary point in the plane. And then we're also going to have that R0 and R are position vectors of 2 points on the plane. So it's of the P0 and P, which we have on our figure over here. And then we have that this R minus R0 is represented in the 3D figure by P0P. And so then the normal vector n is orthogonal to every vector in the plane. That means that it's also going to be orthogonal to this R minus R0, because the R minus R0 is this in the plane right here. In particular, it's right here, R minus R0. And so with this, then we know, since what we learned last time was that dot products are important about orthogonality, that means the dot product of these two things is equal to 0. So this gives us a vector equation of the plane that n dot r is equal to n dot r0. So this is a vector equation of the plane. And so we can also get a scalar equation of the plane. So to do this, we would actually take the dot product that we have right here. So we would say, okay, let's call this normal vector ABC. And then we're going to call R as equal to X, Y, and Z. And then we're going to call R0 as equal to X0, Y0, and Z0. And then if we do n dot R minus R0 in this case is equal to 0. So this was our vector equation for our plane. What we're going to get when we actually multiply this out. So if you did the ABC dot X minus X0, Y minus Y0, and Z minus Z0 is equal to 0. What you're going to get is then that A times X minus X0 plus B times Y minus Y0 plus C times Z minus Z0 is equal to 0. So this is the scalar equation for the plane. Through the point P0 of X0, Y0, Z0 with the normal vector n is equal to ABC. And so as an example, if people want to do a quick example to make sure that you followed, then find the equation of a plane through this point 2 for -1 in 3D space with a normal n as equal to 2, 3, 4. So then if we say, okay, that seems great. So at this point, I could say these are the X0, Y0, and Z0 in this above equation. And then this is going to be the ABC in the above equation. And so you can do some direct subbing here, and it will give you 2 times X minus 2 plus 3 times Y minus 4 plus 4 times Z plus 1 is equal to 0. Or what you would get is 2X plus 3Y plus 4Z is equal to 12. And so we can see that this is an equation of a plane. For people familiar with optimization, you can see that this kind of looks like a equality constraint. And so that's partly where the utility of this comes in. So then we are collecting terms. The equation of the plane is going to be like this: ax plus by plus cz plus d is equal to 0, where we would get that the d is equal to the negative ax0 plus by0 plus cz0. And so this is a linear equation in x, y, and z, because each of those variables is only multiplied by a constant. And so yeah, if A, B, and C are not all 0, then the linear equation represents a plane with a normal vector ABC. And so some interesting things, you can say that, oh, sorry, one thing I wanted to point out, you can sort of see the ABC really quickly. So you can see that in this equation for this plane right here, we can really easily see the normal vector. And so that's great. And then we can also say that planes are parallel if their normal vectors are parallel. And you can also get the formula for the distance from a point to a plane. And so there you go. That was where I was trying to go on last class. So now you have it. And so sounds good.